In the previous two lectures describing analysis of variance, we talked about the basic ANOVA idea, some experimental design, and actually how to analyze and test in a one-way ANOVA experiment. Now we're going to talk about some things we need to be careful of, some due diligence to make sure that we're not doing this sort of thing, trying to fit a square peg in a round hole. We call this model checking. ANOVA operates based on two assumptions that are baked into the ANOVA model. First off, that the effects of treatment are linearly related. That is, each treatment has an adjustment away from the grand mean. And each observation follows the group mean plus or minus some small amount of error, and we assume that that error is normally distributed and it has a constant variance across groups. So the F statistic is based on this because it assumes a ratio of chi-square variables to form the F distribution, which in turn assumes normally distributed data. So we want to go from Z to chi-square to F. And the Z is what gets us. In addition, the mean squared error, the one that we use in the denominator of the F statistic, remember F is the mean square for treatment, divided by mean square error, is actually a pooled variance, which assumes homogeneity of variance. That's that equal variance across groups. We're going to look at a bad example to see how that plays out and what we can do about it if we see this in an analysis. So that normality requirement translates into normally distributed residuals. Oh, that's that epsilon ij part. Okay. And we can check this either graphically with a QQ plot or with some sort of hypothesis test, for instance, the Shapiro-Wilk test. So here's an analysis. The residuals are not really conforming to the straight line. And if we run this Shapiro-Wilk test, we get a really small p-value, so not normal. Ouch. So one assumption violated. The other assumption, of course, is homogeneity of variance. And if we just look at a box plot of our groups, we can see that we're probably already in trouble because we see really small variation here and really large variation here. But this is really not conclusive, so we'll do a hypothesis test. Bartlett's test is a good test for that, for homogeneity of variance. And we see we get a really small p-value there as well. And so, ooh, not homogeneous. Double ouch. Now, why is this important? Well, this is important because it says our original ANOVA may not be credible, and our estimates of error are probably off. So what if the data fails the test? Well, there's a couple of different approaches. One is go around it. And we could do that by using a non-parametric test, for instance, the Kruskal-Wallis test. This is a generalization of the Wilcoxon-Rank sum test we spoke about in an earlier lecture, but it does require post hoc comparisons. The reason we can do this is distribution free. So normality is not a problem. That's one way. The other way, which maybe gives us a little more flexibility, is what's called a variance-stabilizing transformation. In the vernacular, we call this torturing the data. Okay. If we do this successfully, we can run the ANOVA on the transformed data. And once we do that, we can use all our standard post hoc tests. Of course, doing this is a little more of an art than a science, and I'll show you how that works in a few minutes. So here's the idea of a variance-stabilizing transformation. Okay, engineers love this one. If the variance isn't stable, take the logarithm of everything. Okay, and logarithm is nice because it maintains order of measurements. A mathematician would call that a monotonic transformation. Biologists like the square root transformation. And that too maintains the order of the measurements. And so it's another monotonic transformation. But these are just two examples of a much more general approach. The general approach is embodied in something called the Box-Cox transformation. The transformation says find a power to raise the data to, okay, and so there's that power, lambda, all right? And so here's their official transformation. We take the data, raise it to the lambda power, subtract off 1, and divide it by lambda when lambda is not 0. Well, if lambda is 0, anything to the 0 power is 1, subtract off 1, and you get 0. You get 0 divided by 0. 0 divided by 0. No way. Don't want that. But it turns out that under certain conditions, as lambda goes to 0, this converges to the natural logarithm, which is a lot simpler. Now, the Box-Cox transformation will let us find some acceptable values for lambda with a numerical algorithm, which we will not go into. It's fairly complicated and extremely boring, so we won't talk about that. But granted that we can find that lambda, we'll just transform the data by raising it to the lambda power, since y to the lambda is just linearly proportional to the official Box-Cox transformation. So linearly proportional. So this is one of these things where we can let the computer do it. Finding it numerically, by the way, in the mass package, R has something called Box-Cox that'll let you do that. So let's look at our example. Now let's talk about the two ways to get around the problem of failing the assumptions. So the simple alternative, we'll just use the Kruskal-Wallis test. There's the way to do it in R, just called the Kruskal test. We get the rank sum test. We get a really small p-value. This tells us the means are not equal. And so we'll reject H0. ANOVA is done. Of course, to do post hoc tests, we need to do rank sum tests, 2 at a time, probably with a Bonferroni adjustment. Okay, or we can do it the scientific way with a Box-Cox transformation. If we run it in R, the preferred way is to get this graphical summary. So graph from R. And this shows us the quality of the transformation. More is better. And prints out a 95% confidence interval. And so our lambda that we want is somewhere in there. Okay. If we look at this thing, we can see that a couple of simple fractions are in there, 0.25 or 0.5. Okay. The reason to use simple fractions is, how do you explain lambda equals 0.314159 to a scientist? You probably can't, but have fourth roots or square roots, things like that, even cube roots, are pretty easy to explain based on physical or biophysical properties. So we might want to keep that in mind when we pick a transformation. So in this case, the data was transformed with lambda equals 0.5. That is a square root transformation. Okay, and then it was tested, and wow, normal residuals, almost equal variances, the hypothesis test testing each of those both had very, very high p-values, and so this said that the data is adequate for being applied or analyzed with ANOVA. Remember, it doesn't need to be perfect. Just good enough.